All right. Are you guys ready?
I'm ready. Yep.
All right. So, my research presentation is on trying to quantify clusters formed by electrodeposition. So the overall goal of this project was to quantify these characteristics of clusters grown by electrodeposition, so I can compare them to other clusters, specifically other clusters that are formed by different forms, like let's say not using electrodeposition. So we can kind of better understand, what is causing these to, grow like the way they are. So just a little bit of background on what electrodeposition exactly is. It consists of a cathode and an anode, some sort of electrolyte solution, and a voltage difference. So it consists of putting the cathode and an anode in the solution itself, and just by applying a voltage difference, the ions in the solution will aggregate or form on the cathode. So this has a couple real world applications, but specifically I used it for particle aggregation. So here's a picture of what the setup itself looked like, where on the right, that's where the little cell is, where the electrodeposition is actually occurring. And that's a digital camera hooked up to a laptop, so you can see a little closer where what is happening inside of the cell. So in a paper by Santos and Santos titled A Fractal Dimension Minimum in Electrodeposited Copper Dendritic Patterns, they did this process using copper everything. So they used electrochemical deposition with copper, copper wire cathode that they put through the center of a petri dish, a copper wire ring that acted as the anode, and they submerged that in copper sulfate solution. So all sorts of copper. They were able to create pretty much a two-dimensional environment for these particles to aggregate when they applied a voltage difference. So this is kind of the basis of what I did, how I grew the clusters, and I replicated their methods and their steps that they did, which was shown in the last image. So here on the right, it's not the greatest resolution, but they grew 6 different types of clusters, all at 1 molarity. And then the top left is 5 volts, and then it just goes up by 1 volt, 6, 7, 8 volts, 9, and then 10. And then those are the general shapes of the clusters they grew at those varying voltages. So what I decided to do was to vary not only the voltage, but also the concentration. So I picked a couple different sets of concentrations and voltages shown by that table over there. 4 specifically is what I started with. 0.5 molarity, 7 volts, 0.5 and 5 volts, and then switched over to 0.25 and 7 and 0.25 and 5. So I planned to grow multiple clusters under each specific parameter set, and would hope that that the clusters grown in those sets look similar to each other in the sets, but different from the different sets. So here are 2 clusters grown at the 0.25 molarity and 7 volts. Just kind of eyeballing it, they look pretty similar to each other. They've got, looks like a similar amount of branches. They look kind of equally complex. They branch in similar ways. Whereas these 2 clusters, grown at 0.5 molarity and 5 volts, they look very different from the last 2, but they look similar to each other. So just that small change in voltage and concentration affects how the cluster will grow pretty impactfully. So these are all examples of fractals, where a fractal is just a shape in which the whole is similar to the parts. So there's a couple really effective ways to describe fractals, because it's easy to sit here and say these look similar to each other but different from these, But to actually have a number to describe this is why they're different or this is how different they are is a little more complicated. But a couple ways we can describe fractals in general are the fractal dimension and lacunarity are two specific ones I picked. So fractal dimension is nothing more than a measure of complexity. How complex is this shape or this fractal? So fractal dimension for a line would be 1. It's not very complex, and it's one-dimensional, and it would equal 2 for a plane. Twice the dimensions, twice the complexity. So fractal dimension is a form of a scaling rule where n equals r to the d. The number of parts is equal to the radius to the fractal dimension or dimension in general. So a better way to kind of think about this is imagine a two-dimensional box. A box is two-dimensional, and if we want to measure that box with a smaller box, let's say half its size, its measure, n, is then going to be 4. It's going to take 4 of those little boxes to fill the big box, and its scaling factor is 2 because the smaller box is half the size. So that would be 4 equals 2 to the d, and dimension, if you solve for d, it would be 2. You have 2 dimensions. That's how complex the shape would be. So when we pick significantly more complicated shapes like fractals, that number gets a little more interesting. So that's really nice when you have those easy numbers. You know how many parts you have or the radius. But it becomes a lot more difficult when we're working with something like a fractal that we saw earlier and you don't really have those numbers handy. So the best way to do it is the box counting method, which we can talk about a little bit more. Another interesting descriptor would be lacunarity, which is essentially just the gappiness. Similar to the word lake is, I believe, where it came from. So I was hoping to use these two quantities to attach to each fractal I grew and describe it that way. So actually doing that required a bit of image analysis. Specifically, I used a free plugin for ImageJ called FracLac. ImageJ is a pretty popular open source Java program that has lots of plugins for a bunch of different things, and they just so happen to have one on all sorts of fractal analysis. So FracLac stands for fractal and lacunarity. So this is pretty important because it's where the box counting method that I previously mentioned comes from. It's able to do it. So going a little more in depth in what the box counting method is, here on the right is an image of one of the fractals I grew and the box counting method in action. So the general idea behind it is the boxes with the main element. You start with just a couple big boxes at the start, and then you get smaller and smaller. So the boxes with the main element, in this case the white pixels, they stay. And if you have a box that only has background or black in it, then you get rid of that box. And then you shrink the box a little bit and repeat that process until you have essentially the shape in the form of a bunch of little boxes of your shape. So here's kind of a zoom in on a branch of the last two slides of that process, because it gets a little small and it goes a little quick. So here you see this is the last step. The bottom is the final process. That's all your boxes, and those boxes essentially make up the shape of what the fractal is. So the box counting method is then able to take a relationship between the number of boxes, little boxes you have, to their size, and then it spits out a fractal dimension. The equation itself is fractal dimension is the limit as the size of the boxes goes to 0. So as the boxes get smaller, you take the log of the amount of boxes over the log of their sizes. And that should be a number between 1 and 2, because it's not quite a square, it's not quite a line. So this is what FracLac gives you after you run the box counting. So all that image happens in the background. Once you scan it and go, this is what it gives you. So that's the image itself on the left that we're analyzing. And we're just mostly interested in this top half. So here's the sample data file. What happens here is the box counting is run 12 times, and each of those lines represents one run of it. And then on the right, it gives you a fractal dimension for each run. So you get a slightly different fractal dimension depending on where the box counting decides to start. It doesn't vary by much, but it is like they're all 1.2, but then it varies by 1.22 to 1.29, and in some cases slightly more. So the more times you run it, hopefully the more accurate of a fractal dimension you can find. So I went ahead and averaged all of those for each. I thought 12 was a good number. It was also the default, but that's all changed what you want to do. And R squared on the right, to the right of it, is the correlation coefficient, where 1 is perfect correlation. So essentially what it means is we want a number as close to 1 as possible, and that will tell us how accurate the associated fractal dimension will be. So all those are incredibly close to 1, so that's definitely a good sign. So here is kind of in a different format, 3 different clusters, all at 7 volts and 0.25 molarity. And their associated fractal dimensions that all 12 of those numbers averaged over 3 different time increments, 10 minutes, 15, and 20. And then cluster 2, 10, 15, and 20. So a couple interesting things we can see about this. The fractal dimension is increasing with time independently for cluster 1, 2, and 3 every time. And that makes sense. If you think about it, the cluster is becoming more complex as time goes on. And it makes sense for sure with such a small amount of time. Like the cluster isn't reaching a really big size. We might expect for that to maybe not increase as much as the cluster gets bigger, but I'm not really sure. And each fractal dimension at the same time, so cluster 1, 10 minutes, cluster 2, 10 minutes, and cluster 3, 10 minutes, are very similar to each other. They're very consistent within plus or minus about 0.01. So that's good. That means we can assign potentially a fractal dimension that we'd expect for these parameters of voltage and concentration. And it's very consistent no matter where you look at it, if it's at 15 minutes or if it's at 20 minutes. So potentially the consistency of that fractal dimension indicates we might be able to attribute an expected value for these parameters. So kind of a little aside from the main goal I had of quantifying these clusters, let's take a look at, here's one cluster taken in 5-minute increments. First one at 10, 15, 20, just kind of zoomed in the top left. If you look at the middle branch, the shorter one, between 10 and 15 minutes, we'll look at that one, that branch. After 10 minutes, it clearly grew that length from the cathode, from the center. After 15 minutes, the second picture, eyeballing it, it looks like it grew a little bit longer, maybe got a little bit thicker, but the other branches around it got significantly bigger and thicker. And then again at 20 minutes, looking at the same branch, it doesn't look like it grew at all that time, whereas the other branches clearly continued growing. This is nothing new. It's kind of expected due to the larger branches kind of shielding the shorter ones. This could happen from a number of reasons, including just kind of general blocking of the direction in which the copper ions from the solution can reach the branch, or potentially from local electric fields interfering with the shorter branch. Since the copper ions are conductive, the fractal is part of the ever-growing cathode, so there's all sorts of local electric fields that can be assumed happening. So I wanted to kind of visualize this a little bit better. So I overlaid these images at these varying times and kind of color coded it. So you can see it's the same cluster from the last slide, but only the 10 and 15 minute sections, where the red is after 10 minutes and the blue is after 15 minutes. So that middle top left branch, that shorter one, clearly didn't grow very much between 10 and 15 minutes, whereas the blue on the other longer branches grew significantly more. So I thought this was kind of an interesting way to visualize that a little bit better. And then here's another example of it, of just a different concentration and voltage, and this time with 3 different increments, 5, 10, and 15 minutes. So you can kind of see where the branches stop growing and where they continue to grow. So kind of in general, in conclusion, I was able to grow a lot of clusters under 4 different parameter sets in 2 dimensions. I varied the voltage and concentration to get these 4 different parameter sets. And then I was able to analyze these clusters in FracLac and get some really useful information, pretty consistent fractal dimensions within each set. I was able to get the lacunarity as well for a couple of them. Kind of ran out of time to actually look at it, other than this is the lacunarity. Not quite sure if it makes sense, but it's able to get those numbers at least. And I was able to visually show this shielding that occurs with these pretty pictures. So yeah, that's mostly it. Were there any questions?
Yeah. What was the difference between the different concentrations? Like, what differences did you see? And I'm sorry if I missed this.
Oh, that's fine. So in general, I'll go back to... So in general, it affected a couple things, how the branch showed up, but when I was in the lab growing them, it clearly had an effect on how quickly they grew. I didn't look into specifically how it affected it in that way, how quickly it grows, but just think of it as, there's more ions available to attach, so more are likely to attach. I wasn't able to grow enough clusters at enough different parameter sets to be able to show the difference between the impact voltage has versus concentration. I was just able to show that voltage and concentration in some combination of each other impact how they grow, if that kind of answers your question.
Yeah, it does. I have one more for you.
Oh, go ahead.
Where did you find FracLac?
So the original thought going into this semester was that I was going to write my own image processing software, and that sounded really fun, but after looking into it a little bit, that was not fun. And I think Dr. Binns had pointed me in that direction, because I had talked to him after class once, and he mentioned that I might find something like that on ImageJ, and then just a couple Google searches of fractals and ImageJ, it comes right up. So it's actually a really incredibly complicated and, I should say, comprehensive program. It can do all sorts of things. I just kind of barely scratched the surface with what it could do.
Thanks.
Yep. Any other questions?
Actually, I have an observation.
Okay.
I'm kind of surprised that it looks like if you really observe where the growth is occurring, it appears to be at the end of these kind of dendritic tentacles, or I don't know what you want to call them, dendrites, or
Mm-hmm.
there's. So you proposed two different mechanisms for why one of these dendrites might not grow so much. I think you talked about shielding,
Mm-hmm.
and also the way the electric field might be impacted by surrounding dendrites and such.
Mm-hmm.
Um, yeah, just looking at this, I'm not so sure that the shielding really makes sense, because I can see portions of that cluster that aren't growing that have accessibility to this, large accessibility to the perimeter,
Yeah.
and also to the ions, I guess, in the solution. So my just based on what I've seen here, it would seem to me that the electric field might be a more likely mechanism to explain why you're seeing that particular type of growth. Does that sound reasonable to you, or?
Yeah, that sounds pretty reasonable, especially with this second picture where you have that. Yeah.
Yeah, I was just looking at that right-hand side, and there was a big hunk of that kind of core part that didn't grow at all, and yet it had very high accessibility. Now, I'm not sure if I'm articulating this correctly, but that was kind of my amateurish take on it.
Mm-hmm. I know in the Santos and Santos paper, they reported on this happening. The other thing I could think of is it's a combination of things where, depending on what voltage and concentration you're growing the clusters at, you can expect a certain amount of branches. Where when you're at these low concentrations, you usually get less branches, and then when you get higher, you get more branches. So it could be that playing a role in the fact that on the right-hand side there, you're not getting much growth, but they don't get into too specifics about other than what they think it could be happening. So yeah, I agree where I don't think that necessarily either of those would answer the question unless the electric fields are playing a much bigger role.
Did you see any evidence of kind of filling in with the core areas? I mean, just looking at the image you have there, I don't really see any of what I would expect to, the kind of filling in and increasing the fractal dimension. I just see the growths on the ends of those main branches, those main arms.
Mm-hmm. Well, it could be my when you zoom in a bit more, you can kind of see there's a little more growth in kind of thickness around each of the branches that you don't get quite a good look at from kind of this zoomed out. But yeah, that's
There's maybe like a little bit of a red and blue fringe there that I just can't see.
Yeah, exactly.
Okay.
Yeah.
Okay.
I think if you were to zoom in on this one, not really sure if I can zoom in or not. You see it a little bit better. Where
I can see some of that now.
Yeah, where the growth isn't actually just at the tips, it actually thickens slightly.
Okay.
Any other questions? So I guess if anyone's interested on hearing where I wanted to go next, because I kind of ran out of time. I was still adding to this presentation up until as long as I could, because if you noticed, I talked about lacunarity, but didn't do much more other than I said I could find it. So I kind of wanted to, I think growing more clusters under varying voltages and concentrations, getting more diverse of a pool of clusters would help a lot in kind of looking at trends as well as comparing lacunarities between a few. So I included kind of growing these clusters was a little bit of an art that took some time to get used to and to get down. These are just two images I took pretty early on. I think one of the first couple days where I was like, these are good images to analyze, where the wire ended up being way more of an issue than I thought it would. I tried a couple things on the left. It's the wire straight up. The camera focused on it a little bit, so it made it a little blurry, which kind of messed with, it thought the whole center area, way bigger than what actually is in FracLac. It thought that was part of the cluster. So then I tried moving the wire to the side, and if you look at that, it looks like that's just another branch, so that's what FracLac thought it was. So that alone made my first day of images kind of useless. And then that was just one issue of many. The next thing I ran into was the shadow. All the images before didn't have a shadow, but if you look at the one on the right, it has a shadow. Just like before with the wire, FracLac thinks that's part of the cluster because you have to switch it to a binary image, so it associates that with not white. So that alone, the next day of clusters was useless because they all had shadows, which was as simple as putting the Petri dish environment on top of an extra Petri dish, and then that magically solved the issue. And I included kind of the step-by-step instructions for how I created the images, because believe it or not, those images took a long time to figure out how to create, as well as using FracLac. Like I mentioned, it's as easy as pressing a button. Yeah, and that's all I've got.
Okay, thanks a lot, Jake.
Yeah, thank you guys for coming.
Anybody have any other questions for him after seeing those last few slides?
No questions, but I think it was a very nice presentation.
Thank you.
Some of what you just glossed over there at the end, I certainly appreciate. It might look simple, the end result, but I know there's a lot of work that goes into getting those results.
Yeah. I think I tried at least two completely different methods of getting the images before I came across, just one afternoon I tried something different and then it all just worked. So.
Welcome to research.
Yeah.
Okay. Well, Jake, I would appreciate it if you would send me your final version of your slides.
Oh yeah, sure thing.
Okay.
Like I said, I was working on it until 5 minutes before, so sorry I didn't send them to you earlier.
That's okay. All right. Okay, well,